So, welcome everybody to the fourth lecture of wireless communication course. In today's lecture, we are going to continue talking and explaining wireless propagation characteristics. Basically, we are going to explain statistical multipath model of narrowband fading. The outline of this lecture is going to be as follows. First, we are going to review quickly what we took in the previous lecture. Then we will talk about random multipath model. After that, explain time varying channel impulse response. Then narrowband fading model, and then discuss in phase and the quadrature phase signal components of the model that we are going to explain, and then explain to you how to calculate the auto and the cross correlation of received signals. So, quick review of what we took in the previous lecture. We discussed initially about path loss, and we said that the main cause of path loss is the distance. As the signal propagates through the air, the received signal at the receiver side gets degraded inversely in a way which is inversely proportional to the d square, the distance square. And we said plus path loss, there is a phenomenon called shadowing, which can be modeled as log normal random variable based on the central limit theorem. And we said that central limit theorem states that the distribution of a large number of random independent variables tends to be Gaussian. And this is a phenomenon that we need to always remember. Simply like this, assume you have large number of independent random variables, and I ask you to find their distribution. The distribution is usually Gaussian, and that's why we model shadowing in most of the cases as log normal. Normal means normal Gaussian distribution, and log, it's like a mathematical operation that can simplify your calculation or simplifies your modeling. So, consequently, when you combine path loss and shadowing, you get a model which is given as follows. Yes, everybody remembers this model that we talked about in the previous lecture. PR is the received power of the signal. PT is the transmit power, and this is given in dB, is equal to 10 log 10k minus 10 gamma log 10 d over d naught, where k is a constant you can obtain from your modeling, and gamma is also another constant that determines the slope of your model, and then minus psi dB. Psi, we said, it's a variable corresponding to shadowing phenomenon, and this, since it's random by nature, we model it by log normal distribution, where n represents Gaussian distribution with mean equal to mu and variance equal to sigma square. So these are the parameters. I define them to you one by one. You must be clear about all these variables and remember what their meaning is. If you want to exactly know their meaning, you can refer to the book that I shared with you. So mu psi equals 0 when average shadowing incorporated into k. If you consider the mean to be calculated here, then the mean of your shadowing will be 0. Usually, the mean, either you left it to be modeled in the shadowing formula, or you consider it part of k, and in such a way that the mean of your shadowing will be 0. Now, after you get the model, you can find the outage probability, and we said the outage probability is the probability that your received signal falls below certain threshold, and this threshold is the point at which you can decode your signal successfully. If your signal falls below that, you cannot decode, and we describe the situation as outage. For log normal shadowing model, for log normal, since we have log normal distribution, so what would be the outage? The the probability that the received power at distance d less than the minimal power required to decode your data successfully, which is equal to 1 minus q function. Everybody knows q function, which is the q function is the cumulative function, the error control. Like when you have Gaussian distribution like this, yes, and tell you what's the probability that you are in error, you are below this threshold. This threshold is lambda, let's say. So you need to integrate it from this lambda till infinity. Yes? And this integration, the Gaussian distribution has a term that has this exponential to minus x squared. And you need to integrate this. Mathematicians know that there is no such a solution, closed form solution for this integration. Nobody can integrate this. Everybody has taken calculus 1, 2, 3. You cannot integrate this function. Integration, if you know anybody can integrate it, let me know. Exact form. You have the Gaussian distribution has something like this: e to minus x squared. So when you want to integrate it, there is no integration for it. So how to find the value of this? You find it numerically, and we call this q function. Like you take it from q table, and you say at this value. If you want to integrate at this value, you will get this result. Q of this value equal to this. And from the table, whatever value you get, you just put it and substitute it, and you find the probability. So everybody understands what's the Q function and how is it related to Gaussian distribution. This is basically the error. The error is the probability that it's below this threshold. Your received power below this tail or this. It's something like this way, and you just find the Q function and substitute it and find the probability of outage. So now, how do we find these parameters k and gamma and psi? That was the question. That was the goal of the lecture. How do you find this for shadowing? We said that you use spectrum analyzer or handheld spectrum analyzer, and you go away from the transmitter certain distance, and you record your data. You record the power you receive at this distance, and you go at a different position with the same distance and different distances, and you measure your received power. After you record these measurements, you go to the lab, you open MATLAB or any software in which you can use fitting and modeling methods, and you plot these points, the received power versus the distance. You say that at this point, at distance equal 100 meters, the received power was, for example, minus 80 dB. Yes? And you just plot this point. You plot the other point. At 100 something, 110, you receive different power. You receive different power. At a different distance, you receive different power. At the same distance, at just same distance but different circumstance, you will receive different power. So at the end, you end up getting these points, yes, and you want to find a line that can fit or model these points in such a way that the error is minimal. So when you try different curves, you try different lines with different parameters, and then you end up having a linear model of two parameters, k and gamma. K represents the intersection with the y-axis, and gamma represents the slope of the linear line. And this, when you substitute them here, you calculate basically the model you have, the path loss shadowing model. best fit line through dB data. This is dB data. There is 1p fitting. 1p fitting when you are interested in finding only gamma, the slope. 2D fitting when you find the gamma, the slope, and the intersection with y, which are physically representing gamma and k. They are constant values. And you use mean square error as a criteria to minimize your error. Yes, you calculate at this mean, at this intersection, what will be the error? The error is the difference between the actual values and your estimated model. For 1D, k obtained from free space at d equals 0 captures means due to shadowing. Now, this is the mean. Shadowing, what's shadowing? Shadowing is basically, see how shadowing is basically this, the green variable, which we call variance. How far after I plot the model with the line that represents the path loss and shadowing, the points I have measured, how far they are from the line, this represents the variance. Shadowing variance, variance of data relative to path loss model, which is the straight line that I obtained with minimum mean square error estimate for gamma. You must know that this is the best you can achieve. Yes. So this is basically path loss and shadowing. Now, statistical multipath model, the other type of the new type of channel impairments that you might encounter when you send your signal over the air. So you have transmitter here, transmitting your signal through the air wirelessly, and you have the receiver RX. So your signal hits this building and gets reflected. Not one path, multiple paths. Yes, because it's electromagnetic signal, you have multiple paths. And another signal hits another building, which is located in a different location that has different material, different thickness. Don't know what's the component of this building, and then get reflected out of that and reaches the receiver. The signal again hits another building and gets reflected. So this phenomenon of reflection, we call it multipath fading. And the signal, when the signal reaches here, you get what? You get multiple copies of the same transmitted signal, but these copies are different from each other in the sense they have different random amplitudes, random phases, random Doppler shifts, and random delay. What's the meaning of this? This signal, suppose you transmitted this signal. Random amplitude, your signal sometimes might reach with a higher amplitude or with a lower amplitude. This is random amplitude. Random phase, the phase of your signal was 90, at the receiver might be 0 or another different phase. Random Doppler shift, the shift here, how much spreading you have from the original frequency. You transmit over f equal 800 megahertz. At the receiver, this should be received at 800 megahertz because your receiver is synchronized at that frequency. Now, sometimes due to Doppler spread, you receive your signal at 810 mega. You have spreading. What's the reason of that? Your signal gets reflected out of a mobile object, like car, like train, like plane, whatever, anything that's mobile. When your signal hits and gets reflected, changes the frequency. Yes. Yeah, of course. If the transmitter or receiver or the environment is mobile, you will get this Doppler shift. So if you put a fan, yes, and you let it run, it will affect your signal. Imagine why the transmitter and receiver, both of them are fixed, but due to the environment, you get this Doppler shift. Yes.
You said that signal
Shifts at a different frequency.
yes, signals one signal or all the signals equal to each other. I mean, you said that first signal appears to be 5 dB, the second one is 4 dB. You mean
At a certain time.
at a certain, so you mean from peak to peak. So this is one signal.
Exactly, at a certain time, because the environment is changing with time. Yes?
Yes, I mean, when the signal is finished, the one signal is finished, or one.
Yes.
So the other one will difference.
Yeah, will be with different things.
This is the difference.
Yeah, exactly.
Not the same signal, the same wave. Not the same wave. Every signal has many waves, or many peak to peak.
Yes, that's right. So when you have this signal, you transmit it at T0, you get this, for example, amplification.
Yes.
The same signal, when you transmit it at T1, you might get this. At different times, you have different.
Yes. So
Yeah, at time, because with time, the transmitter may move, the receiver may move, the environment may differ. Yes? And this is the propagation characteristics. And that's why we call it random. Random is coming from here, that at different times you have different output. So, and you have random delay. Your signal here that hits here and go, you can receive it at time. This signal, this same signal that you have transmitted here, when it reaches the receiver, you can receive it at time equal 2 milliseconds. This, since this is farther from the first, you receive it at a later time. So this we call it delay shift. And you have another. Yes. So if the receiver can resolve them, separate them, if all of them are reaching simultaneously at the same time, they will come on top of each other, and they will cause fading, fluctuation in your signal, because they may add constructively, destructively, and accordingly you get always fluctuation in your signal. It's not constant. Yes. Random components change with time. This is the point that I want to make. At different times, even if you are transmitting the same signal, you receive different responses. Leads to something we call it time varying channel model, channel impulse response. Time varying. The response depends on the time. So this is in words, this is in concept, conceptually. But now mathematically, how do you model that? Response of channel at t to impulse at t minus tau. This is the impulse that you send, for example, right? When you send this to the channel affects its amplitude A, its phase phi n of t, and delay at a different time. And this phi actually ultimately causes the Doppler shift. See? So this is, I explained to you by words. Now how to link them with equation. You transmitted this signal, and this signal gets reflected off many objects that are located at different positions and composed of different materials. And then you transmitted one signal, but you received 100 signals. Why? Because this signal gets reflected off of this object, of this wall, of this building, of your body, of my body, and then you receive multiple copies of the signal. And since it's of many objects, gets reflected off many objects, reaches at different times, at different Doppler shifts, with different attenuation, with different phases. This, from n equal to 0 to n capital, this represents the number of multipaths you have received at the receiver due to your environment. A represents the attenuation to your signal. Phi n represents the random phase. And phi also has the Doppler information, because Doppler depends on your the received signal, the angle of arrival of your received signal, with which direction your signal you receive it. For example, when you are moving in a street, everybody knows that the police uses radar to detect if someone exceeds the speed limit. Is that true? Is that used in your country? Radar to detect if someone exceeds the speed limit and then fine him. So what's the concept? Doppler. What's Doppler? We know from physics, lambda multiplied by frequency equal to the speed of light, c. Now, this applies also to your electromagnetic wave, and to our signal. So you want to measure Doppler. For example, as long as the frequency below a certain level, this means that the driver didn't move faster, didn't exceed the limit. Whenever this f changes to f plus certain amount, this means that the driver exceeds the limit. And that's why they detect and know and capture, take a photo of the car or something so that we can later on follow up with this case. So here, in this case, you just replace c to measure the Doppler, the shift. You replace c with the speed of the car, and f with the Doppler shift. And lambda is the same lambda because you are transmitting the same signal. Then you are able to calculate. And this depends on the angle. For example, if you are perpendicular, the movement of the car is perpendicular to the observation point, then the Doppler is always 0. Yes, because it depends on cosine theta, which is the point, the angle between the velocity, how the car is moving, and the observation point. So if the radar is not perpendicular to you, the radar might not be able to detect whether you exceeded the limit or not. Is that clear? This is practically how it works. For example, just a case, just to make you understand the channel characteristics, we just give that example. But there are hundreds of examples similar to this. But the point that I want to make and emphasize here, that you understand the response here, you understand its meaning. H, this you can call it H or C, channel. We either represented by C, the first letter of channel, or H, the second letter of it. So this is tau, and this is time. This is shift, and this is continuous time. T is time when impulse response is observed. At this point of time, I have this response. At a different time, I have different response. T minus tau is time when impulse put into the channel. Time when you transmit your signal. Tau is how long ago impulse was put into the channel for the current observation. Basically, the path delay, the delay spread. I transmitted at t equal 0. The last path that we receive at the receiver, when does it reach? This is tau. Received signal consists of many multipath components. This is what I said here. Many multipath components from n equal 0 to n number. Depends on the environment. Amplitudes change slowly. Phases change rapidly, usually. And due to phases, we may have constructive or destructive addition of signal components. Constructive means they are in the same phase. Destructive, they are out of phase, so they cancel each other. Amplitude fading of received signal. You have here in the amplitude fading, due to this, you get either what we call it wideband or narrowband signals. Wideband channel response or narrowband. If all your multiple paths are reaching the receiver at the same time, there is no delay spread, you get narrowband. If they are reaching in different points, you get wideband. Wideband, at different time shift, you have fading, multipath variations. So I hope we are clear about that up until now. The channel, you have channel, yes. You have up until now how many phenomena? You have path loss. Path loss, we understand path loss due to distance, d. We have shadowing. Yes, due to what shadowing? Due to barriers, obstacles. And this depends on the number of these obstacles and their material type and other characteristics. And here you get what? You get random model of psi, we call it, with different mean, with a specific mean, specific variance. And then we have multipath. This is the complete characteristic. Multipath by itself is many types. It can cause three things: delay spread, Doppler, and fading. Now, when each one have you need to know when does this happen, when does this happen, when does this happen. What are the requirements or the features of the system that can produce such a phenomenon? Delay spread, the meaning of it that your signal reaches the receiver at different time instances, at different channels. Due to what? Due to reflection of many objects located at different distances. Doppler, reflections of many objects that are moving, shifts the frequency. Fading, when all these reflections are reaching the receiver at the same time, they can be added constructively or destructively, making the amplitude to fluctuate. Yes? It's real. Now, there are too much details here, too much details how this happens. In the coming 2 lectures, maybe we'll be only talking about this. Math, concept, theory, practical applications. So it's really very comprehensive and very huge massive subject. So, but now this is the roadmap up until now. There are many details, but this is the roadmap that you need to put it in your mind. Are we clear here? So let's continue. Assume now delay spread. Now multipath also, multipath. This is one classification. There is another classification. See this? Multipath can be classified to narrowband or wideband. This is different perspective. When do we call it narrowband? When this condition satisfies this formula. When this condition is satisfied, we call it narrowband. What does this say? This says that the delay spread, Tn of t, this one, represents the last copy of your multipath that you receive at the receiver, and this is the first. So this is the first copy you receive from line of sight, and this is the last. So the duration between the first and last, this corresponds to this, Tn of t, and this corresponds to this. And the duration between them is called delay spread of the channel. If that duration is much shorter than the duration of your impulse of your transmit signal, the symbol you transmit pulse, yes. If the duration of the delay spread much less than the duration of your impulse, then you have null band. Null band means all your signals, all your multipath reflections reaches the receiver at the same time. And what this causes fading, amplitude fading, yes? So this basically null band has relationship with fading. Wide band, all these. We'll understand in the next lecture how this happens. Wide band, when this condition is not satisfied. Now, nobody asked me about B. What's B? B is the bandwidth of your transmit signal. 1 over the bandwidth is equal to the duration of your transmit signal. Yes, for example, this is a signal. What's the signal? Sine. What's the duration of this? T. Yeah. What's the frequency of this? If I ask you, give me the frequency of this sine. 1 over T is the frequency of this sine. Is that clear? I mean, too much information, yes? Too many details. But they are related to each other and they give you comprehensive understanding of what's going on and facilitate your understanding for the equations. Because the equations, if you go over them and don't link them with this physics, you get confused. You feel they are nonsense, meaningless. Yes? Now, see this roadmap, I know that due to mouse, I'm using mouse, I'm not able to draw it very well, but you draw it in your own way. But the most important thing, you understand it. Once you understand it, you can explain it however you like, in terms of words or visualization. Yes? I'm going to ask you about this in the exam. That's because it's fundamental to check your fundamental understandings. So I see some of you are taking notes, some not. Strongly recommend you to take notes or keep them in your memory and later on record them somewhere. Anyway, I hope the picture is clear what we are talking about. In that sense, when we have narrowband, then U of t, which is something like this is U of t, is almost equal to ut minus tau. So the receiver is not able to distinguish between the signal that reaches a time equal to 0 and the signal that reaches a time equal to t minus tau. This means that they are, with respect to the receiver, all of them on top of each other. If you cannot distinguish the time difference, then this means that you are seeing them, all of them together. So the received signal given by your received signal mathematically is the real part of your transmit signal multiplied by e to j2